Hi everyone. Our project is the Mobile Hydraulic Fluid Conditioning Unit. The members of our team are Robert Bader, Bill Ridge, and Spencer Rehobiak. The advisors for our project are Dr. Chowdhury and Dr. Rodriguez, and our project is sponsored by Parker Hannafin. The agenda for our presentation today is we're first going to discuss exactly what a fluid conditioning unit is. And then from there, we're going to talk about our project's criteria, as well as define the problem. From there, we're going to talk about our proposed solution to that problem, as well as discuss our constructed assembly and discuss our testing data. After that, we're going to talk about our future improvements that we would make on this project, as well as conclude. The first thing we have to do is identify exactly what a fluid conditioning unit does. So our fluid conditioning unit has two main jobs. The first is to filter the solid debris and particles in the system, and the second is to regulate the temperature. So this involves either heating up the fluid if it gets too cold or cooling it down if it gets too hot. There are a few different criteria points we need to meet to successfully be able to complete this project. The first is that the system has to be portable. So that means that it's got to be relatively lightweight and have wheels for ease of mobility. The next is that the system has to be able to be used periodically. So that means that it's not running constantly, but can be used every quarter or even once a year. Additionally, another request is that the system has to be versatile. So that means that it can be used on multiple different types of hydraulic units, such as scissor jacks or hydraulic presses. In addition to versatility, it also has to be used to be able to only filter our debris or only heat up or cool down our fluid, or really a combination of any of three of those options. Lastly, it has to be automated. So that means that the system will function on its own once it's turned on and started. Now I'm going to hand it off to Rob to talk about our problem.
Thank you, Bill. The problem that has been identified is the degrading of oil. This leads to several issues. The first issue with oil degrading is the shortened lifespan of the oil and the machinery using it. This is a result of increased acidity levels. The degraded oil can also act as a catalyst and cause reduced additive performances. Reduced oil performance can lead to decreased lubrication of the system, the potential of valve failure, and restriction of flow. Next is the reduced productivity of the system. This can cause slower starts, increased downtime, and reduce performance of the system. With these issues come other issues such as higher energy consumptions. This is due to the increased torque needed to move the components due to increased friction and wear. Increased maintenance costs due to changing the filters more often, wear on the components, component failures, and shortened lifespan of the oil. The last effect is environmental pollution. This is due to the increased disposal of used oil and having to change the filters more often, and the increased chance of leakage. What causes oil to degrade? There are three main factors that cause oil to degrade. These factors include solid debris, which is generally made up of dirt and fibers which are introduced to the system when it is open, and carbon buildup. Carbon buildup is caused by the excessive heating of the oil and generally happens in the bottom of the reservoir or on the internal components. The carbon can break free from these components, float around in the oil, and be transported throughout the system. This will eventually lead to damage within the various components of the system. Our second factor is liquids. Generally, these liquids are water or different hydraulic oils of other chemical compounds that have been used in the system previously. Our third factor are chemical breakdowns. These occur from general usage of the system and can be caused by heat and friction. Through hours of research and with the given requirements of the system, we have identified our basic flowchart. The conditioning unit will first be attached in line with the hydraulic system that is to be treated and utilize the fluid pump contained within. The fluid will flow through the pressure regulator. This will be used to keep the conditioning components from being damaged by overpressurization. The fluid will then flow through the filtration system to remove any solid debris and onto our thermostat. The thermostat will sense the temperature of the oil and display it on a display. This will be compared to what the temperature of the oil needs to be. The operator will then adjust the directional control valve to control the path of the flow. This valve will send the fluid to be cooled in the cooling system, heated in our heating element, or directly back into the original hydraulic system. The fluid will then continue keeping the hydraulic system working in a more efficient state. With the basic flowchart in mind, we have designed the technical flowchart that goes hand in hand with the CAD model that Spencer will be discussing next. As previously stated, the fluid passes through the flow control valve, which controls the pressure on the system and can be monitored with a pressure gauge directly after it. Once the fluid enters the filter, the pressure in the filter needs to be monitored as it operates at a maximum pressure of 80 psi. With the filter housing being much larger than that of the tubing, it should not be too much of an issue, but something to be aware of during operation. Now into another critical feature. The connectors for the cooling system are going to be quick connect. This allows the selection between the fan cooling component and the optional heat exchanger. The pressure will then be checked again before returning to the original system. This allows the operator to measure the pressure drop through the system and may identify any potential issues that may arise in the unit. Now I will hand this off to Spencer.
Thank you, Rob. To the right, you can see our completed CAD model assembly. There are numerous components on this cart. However, today we have chosen 6 components to go over in thorough detail because these components are the most crucial to the system's operation.
The filtering unit is one of the most important units on the entire cart. This being because it is the first component that the fluid actually flows through. The filtering unit is placed vertically on the cart for the main purpose of being for gravity. When the fluid runs through the filter, it is easier for the fluid to run from the top to bottom and run downward through the filter where gravity takes over and allows it to run out of the outlet tubes on the bottom.
The manual flow valve is located on the inlet manifold. It allows for the operator to choose the flow rate that the fluid is running in through the system. This is manually set and can be adjusted with the turn dial located in the top right corner of the CAD. To ensure the safety of the operator of the fluid cart, it is very important that they look at all the warning symbols for maximum pressures in gallons per minute of flow that we have placed on the cart. This is there because if there is too much flow running through the cart, there would be pressure buildup in the components and we would have some sort of pressure burst that could be potentially very dangerous for the operator. Third is our digital thermostats. Thermostats are really important on a system because they give you the digital thermostat reading of the temperature of the fluid as it is going in and out of the system. This is very important for data collection. It is also very important for the operator. If the temperature of the fluid is too cold or too hot, it has the potential to burst a pipe and cause serious harm. So having a thermostat reading, especially in the direction of the operator, is very important for the safety of the operator. Thermostats are also important to have early in the system because if the fluid comes in too cold or too hot, it could cause catastrophic failure for both the system itself and the pre-existing stationary hydraulic system. The heating unit, or the thermo heater, is one of the most important components on the system itself. The thermo heater allows for the fluid to run through it, heat it up, and then output it, showing the temperature reading on our thermostats. The thermo unit will actually be connected by using quick connects. This will allow us to quickly connect the thermo heater if we decide that the fluid needs to be heated. Described in the next couple of slides, I will show you what will happen if the liquid needs to be cooled.
There are 2 cooling units that are placed on the actual cart itself. They are both on the bottom layer of the cart. The first of which you can see on the right is the cooling unit that is the fan. The fan cooling unit cools the fluid by taking a fan located in the cylindrical part of the cooling unit and blowing cold air onto the fluid as it bypasses through the system. If the fluid is cool enough, it'll then flow back through the system and go out through the outlet. However, if the fluid needs to be even more cooled down, it'll go to the cooling heat exchanger. That'll be explained in the next slide. The second cooling unit is the heat exchanger. This takes coiled water tubing and cools it by having continuous cool water run through the heat exchanger to cool down the hydraulic fluid running through the system itself. This cooling unit is separate from the fan and could be chosen compared to the fan by using a quick connect. They'll both be attached to the system, but only one will be in use at a time.
The finished system assembly can be seen in the photo on this slide. Each component that was described above in the CAD model assembly can be shown in the actual model here. The CAD model only shows the permanent tubing, as the other tubing will be connected via quick connects and will constantly be moved. Quick connects are connections that are attached to components that can be quickly removed by just sliding a lever back. These components are very effective. However, they are slightly less superior to the permanent connections because they have a slight pressure drop because they are actually able to be dismantled from a certain component.
So here's the data for our heating function of our cart. The fluid is routed through our induction heater, which is set at around 200 degrees Fahrenheit or about 93 degrees Celsius. So over the span of this 40-minute test, the fluid increased to just over 8 degrees Celsius. This gives us an average increase of about 0.3 degrees per minute. Here is our data for the cooling function on our cart. The fluid is routed through a series of tubing inside of our cooling fan. Over a span of about a 45-minute test, the fluid temperature decreased just over 1.5 degrees Celsius. So this is an average temperature drop of about 1/10 of a degree per minute. It was expected that the cooling fan system would take longer than the induction heater because it's blowing air over a series of tubings in the fan versus the induction heater that is directly contacting the fluid.
Our initial plan was to make the system itself automated. The team would have completed this by creating a ladder logic flowing diagram, then by implementing the ladder logic into a programmable logic controller, or what is commonly known as a PLC. PLCs are used in almost every technical industry as they allow for an efficient way to automate systems. Our system would essentially make all of the adjustments needed to the hydraulic fluid automatically. This would save an operator from having to reach into the system while it is running. The ideal system would only require the operator to select the input specifications of the oil and then let the system run by itself. However, given timing and COVID restraints, it was decided that the automation of the system would not be a feasible option for this semester. However, it would be an excellent future senior design project.
As this project came to an end, we completed our main objectives. We created a mechanically functioning mobile fluid conditioning cart, which has the ability to heat the fluid up by 0.3 degrees per minute and cool the fluid down by 0.1 degree per minute. By doing this, we achieved our design criteria and finished the project before the deadline.
Thanks everyone for listening. Are there any questions?
Well, thank you, team. Another well-run show.
Nicely done.
Yes. Oh,
Thank
yeah, we're
you.
getting hand claps all over the place.
Oh, here's one.
Okay, the group in your description, you mentioned induction heater. Those were resistance heater, not induction heater. So you might correct that one in your presentation.
Okay.
Hey guys, good presentation.
Thank you.
Thanks, Dr. Rodriguez.
Yeah, great job, guys. You were all really well spoken, and your presentation looked great.
Thank you. Thanks, Tim. Appreciate it, man.
I wanted to say something, and I noted this to a couple of you individually too. Sometimes when we do a presentation and you record it, and people are reading, and it sounds like it's being read, and you guys didn't sound like you're being read. You just really good inflection, liveliness, interest in your voice. It was nice to see.
Thank you. That was the whole goal with recording it, was to try to, make it seem like we were actually, still with you guys presenting. And so that's the whole reason with, I'm going to pass it off to Rob and things like that. So
yeah, no, you did a nice job. And it wasn't sing-songy. Sometimes it gets sing-songy. It wasn't. It was really nice.
Awesome. Thank you so much.